AI FDC is a semi-automated equipment fault detection and classification tool powered by artificial intelligence. It can be viewed as an AI add-on to the traditional FDC, which mainly includes two modules, TPM and MVA. TPM, Trace Pattern Match, is a univariate pattern fault detection approach. It detects faults by evaluating the similarity between the current trace with the reference traces. Next, we introduce the key functions in the FDC system for TPM modeling, following the process of modeling, deployment, and alarm analysis. First, let's see how TPM models can be trained. Enter the TPM modeling menu. Select the process type you wish to monitor. In Sensor Parameters, choose your key sensor parameters. Note that TPM now supports the monitoring of dynamic traces with consistency between runs. There will also be key sensor recommendation functions in later releases. Select historical traces for training. Add tags for the models to be built. Check the number of training runs ready for training. Make sure there are enough traces for modeling. If all the conditions are met, we can start training. Here, we would like to have the normal runs or golden runs for training, so that TPM will learn what normal is. Once trained, users will be able to validate and configure model sensitivity during simulation to optimize fault detection performance. Users can also check the chart of a single instance. This chart can clearly show the abnormal resume. The system will also be able to present multiple instance charts at the same time. After deployment, the models will be able to detect faults in real time. If conventional FDC rules are in place, the system will integrate both rule-based model and trained TPM model for comprehensive fault detection. Once faults are detected, all the data samples will be labeled in red upon the completion of a wafer run. Users will be able to easily compare confidence intervals trained based on normal condition traces and the target trace. The system offers TPM alarm list and details for each alarm in the Alarm Query tab. Users can also view summaries drill down to analysis of TPM alarms based on equipment chamber, process type, sensor parameters, OCAP, tags, etc. Finally, users can check out the TPM chart of each history run in the Process Runs tab under Data Analysis. As we can see from the above process, TPM models can be established without having to define windows or features. They capture normal patterns of each trace and will reflect nuances in trace behavior deviations before any severe faults take place. MVA, multivariate analysis, is a multivariate fault detection approach. It detects faults by evaluating the differences in the joint distribution and between the current set of features with the baseline features. Next, we introduce the relevant functions of the FDC system regarding MVA modeling. The modeling and detection of MVA mainly include 4 modules: modeling, instances, alarm information, and MVA analysis. First, let's demonstrate the MVA modeling function. After entering the UVA modeling menu, select the process and groups you want to model. Groups can be new added, default, or existing ones can be selected. Click the Edit button to switch to the draft version. Add a scene for detecting the selected recipe or product. Add the basic data of MVA in the modeling settings, such as windows, raw parameters, and related summary calculation data. After the basic data is added, start the MVA modeling. MVA utilizes the relationships between features extracted in the traditional FDC process to detect faults based on changes in these relationships, which is more robust to small random variations than single variable detection. Select multiple summaries for addition. Set the desired multivariate algorithm according to requirements, supporting T2 and PCA/T2. Enable detection control, set relevant detection configurations, such as control methods and limit types. Set the sample pull time range and sample sampling method. Set the detection logic and OCAP, as well as limit calculation parameters, etc. After the modeling settings are completed, limits can be set for different scenarios and chambers respectively in the limit settings. Support batch setting of limits, status, reference status, limit calculation, and sample reset operations. Select any chamber to manage sample data and perform chart simulation. Since sample pulling is based on historical data, the summary parameters in the newly created window have not yet generated sample data. Therefore, we switch to the previously defined MVA variable for viewing. On the Sample Data Management page, you can view the overview, dataset, trend chart, box plot, correlation coefficient matrix, and correlation coefficient chart of the MVA variable. On the chart simulation page, limits can be calculated based on the limit settings, and alarm predictions can be simulated to set reasonable limits. Clicking Apply sets the current threshold. After modeling is completed, clicking Publish generates the relevant instance. Instance function. In the instance list, batch instance viewing, limit setting, status update, and other operations can be performed. Instance charts can be viewed. Instance simulation can be conducted. The instance simulation page can perform threshold update operations based on limit settings. Alarm information. After the instance is generated and activated, when the data does not meet the threshold requirements, alarm information will be produced. Alarm list viewing or alarm chart statistics can be performed. Alarm details can be viewed, and alarm status can be set. Batch setting of alarm status can also be done on the alarm list page. On the alarm chart page, statistics and distribution can be viewed by day, week, and month based on different dimensions such as equipment chambers, process types, model analysis, and alarm identifiers. MVA analysis. For the modeled MVA variables, in the MVA analysis page, data within a certain time range can be pulled based on the multivariate model to view the variable overview, dataset, trend chart, box plot, correlation coefficient, and correlation coefficient chart. By monitoring the behavior of the entire system, MVA can detect deviations before any single feature shows significant changes, helping with initial diagnosis.